Hello everyone. Today we are going over topic 3-10, spring force and Hooke's law. So let's just get started here. We're going to start with 3-10 quiz question 1, and I want you to have your formula sheet right next to you as we're going through this. I'm going to go over the relevant equation for Hooke's law and discuss some of the properties of it, and then we'll go through the quiz questions. So Hooke's law associates itself with the equation for springs, which is the force acting on a spring is equal to k, the spring constant, times dx, the change in x, which is the amount that the spring is being extended. So we could also rewrite this as the force acting upon the spring is equal to the spring constant times, in parentheses, the final length of the spring minus the initial length of the spring. And obviously this version here isn't necessarily scientific. I think I'd write it more like k times x sub f minus x sub I, something like that. But you get the idea that you can figure out the change in x by considering final minus initial, the final length of the spring minus the initial length of the spring. We know that the k constant here is specific to a spring, so when considering Hooke's law, this value would either be given or would have to be deduced from other information in a passage for the purposes of a physics class. You wouldn't be required to essentially make a plot of the force versus the extension, and then whatever that slope is. Because if you look at this equation, we can kind of make this look like y equals mx plus b, where b equals 0, x is our change in x, right? And k is our slope. So if you were to want to figure out the spring constant, you can design an experiment where you stretch a spring and then you have a scale that measures the amount of force. So let's say that's 20 newtons, and then it's longer, and that's 50 newtons. You can plot those values on the x-axis being the change in x, and then on the y-axis being the force, and you can plot the values and get the spring constant. And that's one way of deriving the spring constant for a given spring. Given that information, it's important to know this equation in order to just figure out equations regarding Hooke's law. So let's get started with the first question. 3-10 quiz 1. A spring obeys Hooke's law. That's good. When you stretch a string 2 centimeters, the spring pulls on you with a force of 10 newtons. When you stretch the same spring 4 centimeters, the spring pulls on you with a force of ... So this one is regarding, this has two facets to it. Equal and opposite forces, which is one of Newton's laws, and scaling up Hooke's law, or scaling up based on given information. So we know that 10 equals 2k for the first Hooke's equation, because 2 is the change in x, and 10 is the total force. So if we write out our equation, F equals k delta x, we plug in 2 for delta x and 10 for the force. And if we say 2k equals 10, then what does 4k equal to? Well, we doubled the delta x. And if we look at this equation, the force acted on the spring is directly proportional to the change in x, the change in length. So if we double the change in x, then we must double the force acting on the spring. So therefore, 10 times 2 equals 20, and B is our answer. The next question we have here, a spring is attached to a wall. When you pull on the spring with a force F, it stretches with distance delta L. Now the spring is detached from the wall and you pull on one end with a force F. while your friend pulls on the other end with the same force F. What distance does the spring stretch? Hint, consider a free body diagram when the spring is attached to the wall. Okay, well, thanks for the hint question. This is very helpful. So let's draw out the free body diagram for the spring, and we'll consider the spring the same as like an unidentified box. And we'll do it for both of these. So if the spring is attached to the wall, and we apply force F to it, and it's staying attached to the wall, what must be happening? What must be happening between the spring and the wall during this interaction? If the spring is staying in place and we are applying a force, what must be happening on the other side in the opposite direction for the spring to stay at rest and not fling toward you? If you answered an equal and opposite force, you would be correct. The spring would apply, or the wall would apply an equal and opposite force to the spring and rendering it motionless, essentially. And we know that because this force applied to the spring caused a distance of delta L, let's then look at this second spring and look at the forces applied to it. We see that it basically drew out the free body diagram for us in such that the force we have applied, this is our force, and I'm going to put the hash line saying that these are the same length, even though optically they're not, but we all know I'm not a great artist, so in memory, in our imagination, these are the same size. So this is the second spring, and then this is the force your friend, wow, that one is very long. Okay, there we go. And that's the force your friend is applying on the spring. So looking at these two free body diagrams, they look identical. So if this first free body diagram has a stretch of distance delta L, and this second free body diagram is the same as the first free body diagram, and then it must also have a distance of delta L. Therefore, B is the answer. For this next question, I changed the color of my pen so I can better demonstrate what's happening here. So, the graph shows the force needed to stretch a molecule of DNA. Suppose we measure the spring constant of DNA at 3 points. When it was 5%, 75%, and 125% longer than its original unstretched length, which measurement would yield the smallest spring constant? Hint, the spring constant is related to the slope of the force versus extension curve. So as I was explaining earlier, the slope of a distance versus force, a change in L, a change in X versus force diagram gives you your spring constant K, so that's K. If it's changing throughout and you're presumably looking at this graph with a bit of confusion, we then let's begin by plotting the 3 points that are relevant to this question. 5%, which is about a dot right there. 75%, a dot right there. And then 125%, a dot right about there. And maybe that wasn't the best color. I'm gonna make a bright green for this, actually. There we go. That's visible. So let's look at the slopes for each of these points. Looking at 0.05 or 5%, we have a slope that if we just extrapolate based on the slopes around the given point. So we draw a line that touches the dot exactly once, and it's in line with the current slope at that moment. So we can draw a slope that's like that. So we have, this is the slope for 5%. If we look at 75%, it has a less steep slope. So it has a less steep slope. It has something like that going on at that moment. And then if we look at 125%, we have a very steep slope. So those are the three slopes. And let's rank them in terms of their steepness. So 125% is greater than 5%, I'm going to draw the percent signs in, which is greater than 75%. And remember what the question is asking for. I'm going to switch colors back to my famous blue. The question is asking for which one would yield the smallest spring constant. So how would we have the smallest spring constant? Well, if we have a large change in delta x combined with a small change, let me draw a proportional arrow, a very small change in force, that must mean that the spring constant is very small. So, yeah, the k must be small. So therefore, if k is small, that must mean when graphically shown, it must have Hooke's law must have a very shallow slope. And which one of these points has the most shallow slope? Well, it's this point right here. It's 75%. And therefore, B is our answer, because 125% has the highest slope, which means that it has the highest k constant, or spring constant, which then further means that it's harder to pull on this DNA once it's this far stretched. It requires a lot of force to get a little bit of extension, whereas from 0.5 or 50% extended from original length to 100% extended, we see that it takes very little force to stretch a long amount, a great distance. So you basically, from 0.5 to 1, you basically increase this DNA's length by 50%. And that's why B is the correct answer, because it takes very little force to extend it a great deal, which then must mean that the K constant is small. And that's everything I have for you today. Thank you so much for watching, and have a great day.